The astronauts aboard the space shuttle could see the flashes even when their eyes were closed. Bright bursts of light that seemed to pierce through flesh and bone, appearing like fireflies dancing in the darkness behind their eyelids. They called them cosmic rays, but that clinical term did nothing to diminish the unsettling reality that something invisible was passing through their bodies, through the walls of their spacecraft, through everything, leaving only these phantom traces of light as evidence of its passage. On April 24, 1990, the Hubble Space Telescope drifted into position over Brazil, its sophisticated cameras prepared to capture the deepest reaches of the cosmos. Instead, those same cameras suddenly flooded with static, ghostly images washing across the screens in waves of electronic snow. The telescope had gone blind. Engineers on the ground scrambled to understand what was happening, but the telescope itself could tell them nothing. It simply stopped seeing, its delicate electronics overwhelmed by something they couldn't detect, couldn't measure, couldn't fight. This is the South Atlantic Anomaly, a vast invisible wound in Earth's protective magnetic shield. Here, hundreds of miles above the ocean between Brazil and South Africa, our planet's defenses fail. Deadly cosmic radiation that should be deflected harmlessly into space instead pours through this weakness, creating the most dangerous radiation zone that our planet possesses. Satellites stay here silently, their circuits fried by invisible bombardment. Spacecraft must shut down non-essential systems when passing through. And the most disturbing part? The anomaly is growing, shifting, moving across the face of the Earth, and no one can explain why. The instruments began screaming in 1958, high above the Brazilian coast, and nobody understood why. The first Explorer satellites, those fragile pioneers of the space age, carried Geiger counters into the black void above Earth. Scientists expected radiation, of course. Space was hostile, unforgiving, a realm where solar winds and cosmic rays battered anything foolish enough to venture beyond our atmosphere's protective embrace. But as the satellites traced their orbital paths, looping around our planet again and again, the instruments detected something that made no sense. Over one specific region, the radiation readings spiked dramatically, climbing to levels that should have been impossible at such low altitudes. The detectors rattled with activity as the satellites passed over South America and the South Atlantic Ocean, registering doses of charged particles that belonged hundreds of miles higher, trapped in distant radiation belts far from Earth's surface. James Van Allen, the physicist whose name would become forever linked to the radiation belts encircling our planet, studied the data with growing unease. The pattern repeated with mechanical precision. Every orbit that carried the satellites over the South Atlantic revealed the same anomaly, the same dangerous spike in radiation levels. It was as if something had torn a hole in Earth's magnetic defenses, creating a gateway where the fury of space could reach down and touch our world. The discovery posed immediate questions that rippled through the scientific community like tremors before an earthquake. Earth's magnetic field was supposed to protect us, a shield generated deep within our planet's core, deflecting the constant bombardment of charged particles streaming from the sun. The Van Allen belts themselves, those two distinct regions of trapped radiation encircling Earth, existed because magnetic field lines captured and held those dangerous particles thousands of miles above our heads. But here, over the South Atlantic, something had gone wrong. The inner Van Allen belt, which normally maintained a safe distance of at least 600 miles above the surface, dipped dramatically lower. In some places, it descended to barely 200 miles, close enough that satellites in low orbit found themselves swimming through radiation levels that could fry electronics and threaten human life. Scientists named it the South Atlantic Anomaly, though calling it merely an anomaly felt like an understatement. This was a fundamental weakness in the planet's defenses, a magnetic valley where the field strength measured only 1/3 of what it should be. Astronauts passing through the region reported seeing strange flashes of light, cosmic rays striking their retinas directly as the weakened field allowed particles to penetrate deeper. Satellites experienced glitches and shutdowns, their circuits overwhelmed by radiation doses they were never designed to withstand. The Hubble Space Telescope, decades later, would shut down its delicate instruments every time it passed through the anomaly, protecting itself during those vulnerable minutes when space pressed too close. But understanding what existed proved easier than understanding why. The search for answers led scientists on a journey downward, into realms as alien and unreachable as the depths of space itself. They needed to understand Earth's magnetic field at its source, which meant descending in theory and calculation through thousands of miles of rock and metal, down to the churning heart of our world. Imagine that descent. Picture moving through the solid crust, that thin skin of granite and basalt we call home, barely scratching the surface of Earth's vast bulk. 30 miles down, you would pass through the deepest foundations of continents, where rock flows like putty under inconceivable pressure and heat. But this represents only the beginning, the merest introduction to the alien realm below. Continue downward, plunging through 1,800 miles of mantle, that thick layer of semi-solid rock that flows in vast convection currents over geological time. The temperature climbs steadily, reaching thousands of degrees. The pressure builds until it could compress steel into something denser than diamond. The rock here exists in a state unknown to the surface world, simultaneously solid and plastic, flowing like molasses poured across millennia. Then, at 1,800 miles depth, everything changes. The boundary appears suddenly in seismic data, a stark division where pressure finally overwhelms the atomic bonds holding rock together. Below this threshold lies Earth's outer core, a sphere of liquid iron and nickel, nearly 1,400 miles thick, heated to temperatures approaching that of the sun's surface. This metallic ocean possesses no coastlines, no boundaries, except the rock above and the solid inner core below. It flows in complex patterns, driven by heat rising from Earth's center, and twisted by the planet's rotation. Currents and eddies, some as large as continents, swirl through the darkness. This churning ocean of molten metal generates Earth's magnetic field through a process called the geodynamo. The moving liquid iron, electrically conductive and stirred into turbulent motion, creates electric currents. Those currents produce magnetic fields, which in turn influence the flow of the conductive iron, creating a self-sustaining cycle that has protected our planet for billions of years. The magnetic field lines emerge from this buried dynamo and spread outward, wrapping Earth in an invisible cocoon that extends tens of thousands of miles into space. But the system is neither perfect nor uniform. The outer core's convection patterns shift and change, creating variations in the magnetic field's strength across the planet's surface. And here, beneath Africa and the South Atlantic, something unusual happens deep in the iron darkness. Seismic studies revealed the culprit by mapping how earthquake waves traveled through Earth's interior. The waves slow down and bend when passing through regions of different density and composition, allowing scientists to create images of structures buried beyond any drill's reach. Deep beneath southern Africa, at the boundary between the mantle and the outer core, they discovered a massive anomaly, a region roughly the size of Africa itself, where the material appeared different, denser, somehow distinct from the surrounding mantle rock. Scientists call it the African Large Low Shear Velocity Province, though that technical name barely captures the scale and mystery of this buried continent of different stone. This anomaly disrupts the normal convection patterns in the outer core below it. The churning flows of liquid iron that should generate a strong, uniform magnetic field become distorted, weakened, pulled into different configurations by the massive density anomaly pressing down from above. The result manifests thousands of miles overhead, at Earth's surface and beyond, as a region where the magnetic field strength drops dramatically. The protective shield thins, and the Van Allen belts sink lower, following the weakened field lines down toward the planet. The geological origins of this buried mass remain hotly debated. Some researchers believe it represents the remnant of ancient tectonic plates, slabs of oceanic crust that subducted hundreds of millions of years ago and sank through the mantle until they accumulated at the bottom, piling up like snow against a fence. Others suggest it might be a region of different chemical composition, enriched in denser elements, a scar from Earth's violent formation 4.5 billion years ago. Whatever its origin, it has been there for an immensely long time, quietly distorting the magnetic field, creating a weakness that humanity never noticed until we finally climbed high enough to see it from above. The South Atlantic Anomaly is not static. Like everything connected to Earth's magnetic field, it moves. Drift rates measured over decades show the anomaly creeping westward at a pace of 12 to 15 miles per year, following the slow motion of the outer core's convection patterns far below. The region is also growing larger and weaker, a trend that alarms some researchers. Earth's overall magnetic field strength has declined roughly 10% over the past 2 centuries, and the South Atlantic Anomaly accounts for much of that loss. Some speculate this weakening might signal the early stages of a magnetic pole reversal, those mysterious events when Earth's magnetic field weakens, wobbles, and eventually flips, with north becoming south and south becoming north. The geological record preserved in ancient rocks shows these reversals happen irregularly throughout Earth's history, occurring on average every few 100,000 years. The last reversal took place 780,000 years ago, which means we are statistically overdue for the next one. If a reversal is indeed beginning, the South Atlantic Anomaly might represent the first symptom, the first crack in the shield that has protected us for nearly 1,000,000 years. For now, the anomaly remains a manageable threat, more nuisance than catastrophe. Satellites route around it when possible or shut down sensitive equipment during passage. The International Space Station's orbit stays mostly north of the affected region, though astronauts still accumulate slightly higher radiation doses during their missions because of it. Engineers design spacecraft with extra shielding and redundant systems, accepting the anomaly as one more hazard in the already hazardous business of space exploration. But the discovery fundamentally changed how we understand our place in the cosmos. Earth's magnetic field no longer seemed like an unchanging fortress, but rather a dynamic and somewhat fragile phenomenon, dependent on the churning motions of liquid iron we can never see or directly measure. The South Atlantic Anomaly revealed that space and Earth's interior are connected in unexpected ways, that events in the core can create vulnerabilities thousands of miles away, allowing radiation from the void to reach down and touch our atmosphere. We orbit within a vast and complex system, protected by forces we are only beginning to understand, living on a thin crust above an ocean of molten metal that shields us from a hostile universe. And somewhere over the South Atlantic, that shield wears thin, creating a gateway where space radiation descends, reminding us that Earth's defenses, like Earth itself, are temporary, shifting, alive with change. The human eye was never meant to see light this way. Astronauts aboard the Space Shuttle and International Space Station discovered this truth in the most unsettling manner possible, through brilliant flashes of light that pierce through closed eyelids, through skull and bone, illuminating the darkness behind their eyes with cosmic fire that originates millions of miles away in deep space. The phenomenon begins almost immediately after reaching orbit. Astronauts settling into their sleeping bags for the first night in space close their eyes, exhausted from the intensity of launch, seeking rest in the weightless darkness. Then it starts. A sudden flash of white light, sharp and geometric, like a camera flash going off directly inside their brain. Then another, and another. Even with eyes squeezed shut, even with sleep masks covering their faces, even in the deepest shadows of the spacecraft, the lights continue. Streaks of brilliance racing across their field of vision. Pinpoints of white fire. Geometric shapes that shouldn't exist dancing across the backs of their eyelids. These are cosmic rays, particles traveling at nearly the speed of light, remnants of exploded stars and violent solar events, racing through the void of space until they encounter something solid. On Earth, our planet's magnetic field and thick atmosphere shield us from this invisible bombardment, scattering and absorbing these high-energy particles before they reach the surface. But in orbit, there is no such protection. The astronauts float in an aluminum can, and the cosmic rays pass through the thin metal walls as if they weren't there at all. Through equipment, through sleeping bags, through human flesh and bone, through eyeballs, through the optic nerve, through brain tissue itself. When a cosmic ray passes directly through the human eye, it strikes the retina's photoreceptor cells, triggering them to fire exactly as if they had been struck by visible light. The brain interprets these signals as light, creating the flash. But the cosmic ray doesn't stop at the retina. It continues through, ionizing tissue, breaking molecular bonds, leaving a microscopic trail of damage through whatever cells happen to be in its path. The astronauts can see their own cellular destruction happening in real time, translated into beautiful, terrifying light shows. Don Petty, a veteran of multiple missions to the International Space Station, described the experience with the careful precision of a scientist trying to catalog something fundamentally alien. He reported seeing various types of flashes with distinct characteristics. Some appeared as simple points of light, tiny stars winking into existence and vanishing just as quickly. Others manifested as streaks, like shooting stars racing across his closed eyelid darkness. The most disturbing were the geometric patterns, shapes that seemed almost purposeful, as if intelligence guided their formation. Squares, lines, complex forms that lingered just long enough for his brain to begin processing them before disappearing. The frequency of these cosmic light shows varies depending on where the spacecraft travels in its orbit. Most of the time, astronauts aboard the ISS report seeing perhaps a few flashes per minute, a constant but manageable reminder of the radiation environment surrounding them. But then the station's orbit carries them through a region of space where the protective magnetic field weakens, where trapped radiation particles concentrate in deadly bands, the South Atlantic Anomaly. And when they pass through this zone, the light show intensifies into something far more disturbing. Jerry Linenger experienced the full horror of the South Atlantic Anomaly during his harrowing stay aboard the Russian space station Mir in 1997. His mission was already plagued with disasters, a fire that nearly killed the entire crew, multiple system failures, coolant leaks, and collision scares. But it was the passage through the anomaly that brought a different kind of terror, subtle and invasive. As Mir's orbit carried the station into the zone, Linenger closed his eyes and waited. The flashes began immediately, but their intensity shocked him. Instead of occasional sparkles, his vision filled with continuous strobing light, brilliant white streaks, cascading patterns, a fireworks display generated by his own cellular destruction. He described lying in his sleeping bag, eyes closed, watching the cosmic rays paint pictures across his retinas. The flashes came so frequently, they nearly merged into continuous illumination. He tried to sleep, but how could anyone sleep while their brain was being penetrated by high-energy particles? He knew exactly what was happening. Each flash represented a particle with enough energy to shatter DNA strands, to potentially trigger cellular mutations, to increment his lifetime cancer risk by another tiny fraction of a percent. Multiply that single flash by hundreds, by thousands per passage through the anomaly, by dozens of passages during the mission. The math became terrifying. But the visual phenomena were only the beginning. Linenger and other astronauts reported additional symptoms when passing through the South Atlantic Anomaly, sensations that suggested the cosmic rays were affecting more than just their optic nerves. Headaches developed, dull pressure behind the eyes that intensified as the radiation counts climbed. Some astronauts described feeling strange tingling sensations, as if weak electrical currents were running through their bodies. Others reported difficulty concentrating, thoughts becoming fuzzy and hard to hold onto while the invisible particles bombarded their neuron. The psychological impact of this experience cannot be overstated. These were not superstitious people prone to panic or imagination. These were test pilots, engineers, scientists, individuals selected specifically for their ability to remain calm under pressure. Yet the South Atlantic Anomaly challenged their composure in ways that mechanical failures and emergency procedures never could. A fire aboard a spacecraft is terrifying, but you can fight a fire. You can activate extinguishers, seal hatches, take action. Radiation is different. Radiation is invisible, inevitable, unstoppable. You cannot fight it. You cannot escape it. You can only endure it. Astronauts described the unique helplessness of watching the radiation dosimeters climb as they entered the anomaly. The devices measured the accumulating dose in millisieverts, numbers rising steadily while alarms chimed warnings throughout the station. Protocol required them to move to the most shielded areas of the spacecraft, compartments surrounded by equipment and supplies that might absorb some fraction of the incoming radiation. They would gather in these cramped spaces and wait, watching the numbers climb, feeling the headaches build, seeing the light show behind their closed eyelids intensify. The equipment malfunctions added another layer of dread to the experience. Laptops would crash suddenly, their memory chips corrupted by cosmic ray strikes that flipped individual bits from 1 to 0, or 0 to 1. Star trackers, the sensitive instruments that helped the station maintain its orientation, would glitch and fail as radiation saturated their sensors. Even the station's main computers required special radiation-hardened components and error-checking systems to function in this environment. The astronauts watched their tools and instruments fail around them and understood viscerally that the same radiation disabling those electronics was passing through their bodies, potentially causing similar damage to the intricate biological machinery of their cells. Shannon Lucid, who spent 188 days aboard Mir in 1996, described developing an almost instinctive awareness of when the station was approaching the South Atlantic Anomaly. She would feel a subtle change in her perception, a slight disorientation or unease that preceded the intensification of the cosmic ray flashes. Her body had learned to recognize the increasing radiation levels before her conscious mind registered the change, some deep survival instinct activating in response to the invisible threat. Other astronauts reported similar experiences, a sixth sense for radiation exposure that developed over time. They would catch themselves tensing up, preparing for the passage through the anomaly before checking their orbit charts. Their dreams took on strange qualities during these passages, vivid and fragmented, as if the cosmic rays bombarding their sleeping brains were triggering random neural firing patterns that manifested as surreal imagery. The geometric patterns seen during cosmic ray strikes proved particularly fascinating and disturbing to researchers studying the phenomenon. Astronauts reported seeing not just random flashes but organized shapes, lines, and grids in complex forms. Scientists believe these patterns might reflect the structure of the retina itself, the organized arrangement of photoreceptor cells being revealed by the radiation passing through them. The cosmic rays were essentially creating X-ray images of the astronauts' own eyes, projected onto their visual cortex. They were seeing their own cellular architecture illuminated by stellar fire. Mike Massimino, a veteran of 2 shuttle missions to service the Hubble Space Telescope, described the experience as fundamentally changing his relationship with light itself. On Earth, we understand light as something external, photons bouncing off objects and entering our eyes to create vision. In space, light became something that could be generated internally, forced into existence by particles smashing through tissue. The boundary between self and environment blurred in disturbing ways. The long-term effects of this chronic radiation exposure remain incompletely understood. Studies of astronauts who have returned from extended missions show increased rates of cataracts, the lenses of their eyes clouded by accumulated radiation damage. Some astronauts report lasting changes in their vision, seeing occasional flashes even years after returning to Earth. Ghost images burned into their neural pathways. The cancer risk is statistically elevated, though calculating the exact increase proves difficult given the relatively small number of people who have spent extended time in space. What makes the South Atlantic Anomaly particularly insidious is its predictability combined with its inevitability. Unlike sudden emergencies that might or might not occur, passage through the anomaly is guaranteed. Multiple times per day, the station's orbit carries it through this zone of intensified radiation. The astronauts can see it coming on their orbit charts, can watch the clock counting down to the next passage. There is no way to avoid it, no detour available. They can only prepare themselves mentally for the experience and accept it as part of the price of working in space. During the shuttle era, mission planners tried to schedule spacewalks to avoid the South Atlantic Anomaly, not wanting astronauts outside the spacecraft's minimal shielding when radiation levels peak. But for those living aboard the ESS for months at a time, such scheduling proved impossible. They passed through the anomaly again and again, accumulating dose after dose, watching the light shows, feeling the headaches, experiencing the strange psychological effects of having high-energy particles constantly penetrating their brains. Tom Jones, who flew on 4 shuttle missions, described the experience of discussing the cosmic ray flashes with his crewmates. They would compare notes, describing the patterns they saw, trying to determine if everyone experienced the same phenomena. The conversations had an almost dreamlike quality, astronauts floating in weightlessness in the darkness, discussing the alien light shows playing across the backs of their eyelids. It created a strange intimacy, sharing something so personal and so bizarre, an experience that separated them forever from the billions of humans on Earth who would never know what it felt like to see cosmic rays with their own eyes. The psychological terror of the South Atlantic Anomaly stems not from pain or immediate danger, but from violation and helplessness. The radiation passes through everything, respecting no barrier, honoring no protection. The astronauts float in the most sophisticated spacecraft humanity can build, surrounded by technology costing billions of dollars, and none of it can stop particles smaller than atoms from penetrating their body. They are as vulnerable as if they were naked in space, perhaps more so, because they are acutely aware of what is happening to them, watching the dosimeters climb, seeing the evidence of their cellular exposure in brilliant flashes of light that should not exist. This is the hidden cost of space exploration that public relations materials rarely discuss. The inspiring images of astronauts floating peacefully aboard the station, conducting experiments and gazing down at Earth, these capture real moments of wonder and achievement. But they coexist with other moments, darker ones, when those same astronauts lie in their sleeping bags with eyes closed, watching cosmic fire streak across their vision, feeling invisible particles tear through their DNA, helpless and alone, 250 miles above the planet, knowing that this is the price they pay for leaving Earth's protective embrace. On the 14th of December, 2003, engineers at the Japan Aerospace Exploration Agency watched their screens in growing horror as the Adios 2 satellite began to die. The spacecraft had been humanity's eye in the sky, monitoring Earth's climate and ocean temperatures from its orbital perch. It had been functioning perfectly, sending back streams of precious environmental data until it entered the South Atlantic Anomaly. Then, silence. At first, the team thought perhaps a simple glitch, a temporary communication error that would resolve itself. But as hours stretched into days, the terrible truth emerged. Adios 2's solar panels had suffered catastrophic damage. The radiation tearing through that invisible zone above the Atlantic had degraded the panels beyond recovery. The satellite, which had cost over $600 million to design and launch, was dead. Just 9 months into what should have been a 4-year mission, it became an orbiting tombstone, a billion-dollar piece of space junk circling uselessly overhead. The Japanese engineers weren't the first to lose a satellite to the anomaly, and they certainly wouldn't be the last. What makes their tragedy particularly chilling is how preventable it might have been, if only we had understood the danger sooner. Adios 2 passed through the South Atlantic Anomaly multiple times each day, as do most satellites in low Earth orbit. Each passage subjected its delicate electronics to radiation levels equivalent to what you might find near a nuclear reactor. The solar panels, designed to withstand the normal background radiation of space, simply couldn't handle the concentrated bombardment. Cell by cell, their ability to convert sunlight into electricity degraded. The satellite was being killed slowly, poisoned by invisible particles with each orbit. But Adios 2 was just one victim in a growing graveyard. The Global Star constellation, a network of communication satellites meant to provide phone coverage anywhere on Earth, experienced its own nightmare in the late 1990s and early 2000s. These satellites, 48 of them launched between 1998 and 2000, were supposed to last 15 years. They barely made it a decade. The culprit, once again, was the South Atlantic Anomaly. The radiation degraded their critical components faster than anyone had predicted. One by one, the satellites began experiencing cascading failure. First, their power systems would fluctuate. Then, their communication arrays would start producing errors. Finally, they would go silent entirely. The company operating them watched helplessly as their billion-dollar investment died prematurely overhead. Insurance companies paid out massive claims. Engineers scrambled to understand what had gone wrong. And slowly, terrifyingly, the pattern emerged. Every satellite that spent significant time passing through the anomaly was at risk. The technical details of how radiation kills a satellite are complex, but the basic principle is horrifyingly simple. Modern satellites are essentially flying computers, packed with microchips and solar panels and electronic sensors. These components work because of carefully controlled flows of electrons through silicon and other materials. But when high-energy particles from the Van Allen belts slam into these delicate circuits, they create what engineers call single-event upsets. A proton crashes into a memory chip and flips a bit from 0 to 1 or 1 to 0. Usually this causes a minor glitch, quickly corrected by the satellite's error-checking systems. But sometimes, the particle triggers something worse. A single event latch-up occurs when the radiation creates a short circuit, allowing current to flow where it shouldn't. The chip overheats. Components fry. And unlike a computer on Earth, you can't simply reboot a satellite that's suffered this kind of damage. There's no repair technician who can climb up to fix it. When critical systems die in orbit, they stay dead. The solar panels face their own unique torture. They're made of photovoltaic cells, carefully engineered layers of silicon that convert sunlight into electricity. But radiation damages these layers, creating defects in the crystal structure. Each passage through the South Atlantic Anomaly adds more damage, more defects, where sunlight can no longer be converted to power. Engineers call this degradation, and they factor it into their designs. They expect solar panels to lose perhaps 10 to 20% of their efficiency over a satellite's lifetime. But in the South Atlantic Anomaly, degradation happens 5 to 10 times faster than in normal space. Satellites that were designed with comfortable power margins suddenly find themselves running on fumes, unable to operate all their systems simultaneously, slowly starving to death as their panels fail. Faced with this invisible killer, spacecraft engineers have developed an entire arsenal of defensive measures. Modern satellites headed for low Earth orbit are now designed with the South Atlantic Anomaly specifically in mind, carrying specialized radiation shielding that adds weight and cost but hopefully buys survival. The most critical components, the flight computer and power management systems, are surrounded by layers of aluminum or tantalum. Some satellites use spot shielding, protecting just their most vulnerable chips behind thick metal walls. Others employ redundancy, carrying backup systems that can take over if the primary components are damaged. But shielding has limits. Make it too thick, and the satellite becomes too heavy to launch economically. And no amount of shielding can completely stop the most energetic particles. So engineers have developed another defense, one that's both clever and unsettling. Satellites now carry maps of the South Atlantic Anomaly burned into their navigation systems. As they approach the danger zone, automated systems begin a carefully choreographed shutdown sequence. Non-essential instruments are powered down. Memory states are saved to radiation-hardened storage. The satellite essentially curls into a protective ball, minimizing its electronic activity. Some spacecraft go so far as to orient themselves to present their most heavily shielded sides toward the direction of maximum radiation. Then, like a diver holding their breath underwater, the satellite coasts through the anomaly with minimal systems active, hoping nothing critical gets hit, praying that the damage will be survivable. This procedure happens multiple times every single day for satellites in certain orbits. The International Space Station passes through the South Atlantic Anomaly regularly, and astronauts have learned to avoid certain modules during these transits. They move to the most shielded parts of the station. They postpone spacewalks if they can. They know, with an intimacy that ground-based humans can scarcely imagine, that radiation is pouring through the walls, through their equipment, through their bodies. Dosimeter badges track their exposure, accumulating counts of particle strikes, measuring how much invisible damage they're absorbing. The station itself powers down experiments and instruments, following the same breath-holding protocol as the unmanned satellites around it. But even with all these precautions, satellites continue to die. The Hubble Space Telescope, perhaps the most famous satellite ever launched, has suffered repeated computer failures linked to South Atlantic Anomaly passages. During servicing missions, astronauts replaced entire instrument packages damaged by radiation exposure. The telescope's operators have developed elaborate scheduling systems to avoid making critical observations while passing through the danger zone, because the radiation creates false signals in the detectors, cosmic ray hits that look like distant stars or galaxies, but are really just particles from Earth's own trapped radiation. Imagine the frustration of missing observation windows, of losing precious telescope time to this invisible hazard. The economic cost mounts higher each year. Industry analysts estimate that radiation damage from the South Atlantic Anomaly costs the satellite industry billions of dollars annually. That number includes shortened satellite lifespans, more frequent replacements, expensive shielding requirements, and lost productivity when satellites must power down during anomaly passages. Communication satellites that go dark during South Atlantic Anomaly transits create brief outages in coverage. Earth observation satellites miss imaging opportunities. Scientific instruments lose data collection time. And the cost isn't just measured in dollars. Climate monitoring satellites like ARIOS too provide irreplaceable data about our changing planet. When they die prematurely, we lose years of observations that can never be recovered. The gap in our climate records exists forever, a blind spot in our understanding of Earth's environment. What makes this situation truly frightening is that the South Atlantic Anomaly is not stable. It's changing, evolving, and by most measures, it's growing. Satellite measurements over the past several decades show that the anomaly has expanded, covering a larger geographic area. The radiation levels within it have intensified. And perhaps most ominously, the anomaly is drifting westward at a rate of about 20 kilometers per year. Scientists believe this movement is connected to changes in Earth's magnetic field, which has been weakening steadily for the past century and a half. Some models suggest the field is preparing to flip, swapping magnetic north and south, as it has done many times in Earth's geological history. During such reversals, the magnetic field becomes chaotic and dramatically weaker. The South Atlantic Anomaly might be an early warning sign, a weak spot that's growing as the overall field strength declines. If the anomaly continues expanding, more satellites will find themselves passing through it more frequently. Orbits that are currently safe might become hazardous. The careful calculations that engineers use to predict radiation exposure and satellite lifespans will need to be revised. The cost of shielding will increase. Some satellite operators might find that certain orbits become economically unviable, too dangerous to sustain the kind of long-term operations that make satellite communications and Earth observation profitable. We could see entire regions of orbital space effectively abandoned, too hostile for our fragile electronic machines. There's a deeper, unsettling reality here that goes beyond economics and engineering. We like to think of space as the final frontier, as humanity's destiny, as a realm we're learning to master. But the South Atlantic Anomaly reminds us that we're still incredibly vulnerable up there. Our satellites, marvels of technology representing the absolute cutting edge of human engineering, must power down and hide from radiation like frightened animals seeking shelter from a storm. We can't fix this problem. We can't shut off the radiation or strengthen Earth's magnetic field. We can only design around it, work around it, and accept the losses it inflicts. In a very real sense, we're at the mercy of planetary forces we barely understand and certainly cannot control. The engineers who design satellite shielding and shutdown protocols are fighting a holding action against an expanding threat. They share their findings at conferences with the grim camaraderie of soldiers comparing battle scars. They swap stories of satellites lost, of unexpected failures, of new radiation effects they've discovered. And always, underlying these technical discussions, there's an awareness that the anomaly might win. That as it grows and intensifies, there might come a point where no amount of shielding is practical, where certain orbits become simply too dangerous for long-term satellite operations. We're not there yet, but the trend lines are worrying. And in the silent graveyard of dead satellites tumbling through the South Atlantic Anomaly, we can see our future if we don't find better answers to this growing, invisible threat overhead. The flight from Santiago to São Paulo should have been routine. Captain Eduardo Mendes had flown this route hundreds of times over his 20-year career, with the regional carrier, crossing the same stretch of sky above southern Brazil where the Atlantic Ocean meets the coastal mountain. But on that particular afternoon in 2017, something went wrong in a way that defied every protocol in his manual. The aircraft's primary navigation system failed without warning. Then the backup failed. The radio crackled with static so intense it was like listening to the Earth itself scream. The digital displays in the cockpit began showing impossible readings, altitude numbers spinning wildly, compass headings that made no sense. For 7 minutes, Eduardo flew essentially blind, relying on instinct and the position of the sun through his windscreen, until the systems suddenly restored themselves as mysteriously as they had vanished. The incident report attributed the failures to undefined electromagnetic interference. No mechanical fault was found. No explanation was offered. And Eduardo, Like dozens of other commercial pilots who fly over South America, learn to accept that certain corridors of sky, above certain cities, simply behave differently. They don't talk about it with passengers. They rarely discuss it, even among themselves. But they know. They adjust their routes when possible. They double-check their instruments. They fly with an awareness that beneath them lies an invisible anomaly that has been bathing millions of people in radiation for as long as humans have lived in these places. The South Atlantic Anomaly stretches across the sky like a vast, invisible wound in Earth's magnetic shield. At its most intense point, directly above major population centers, including São Paulo, Rio de Janeiro, Brasilia, and Buenos Aires, the protective barrier that normally deflects harmful particles from space becomes paper-thin. Here, at an altitude where commercial aircraft cruise, radiation levels can spike to 10 times what pilots experience on routes elsewhere in the world. The charged particles that should be swept away by Earth's magnetic field instead plunge downward, penetrating the atmosphere, bombarding satellites, aircraft systems, and everyone beneath. São Paulo sprawls below this weakened shield, home to more than 12 million people in the city proper and over 22 million in the greater metropolitan area. These millions go about their daily lives, commuting to work, raising children, building careers, entirely unaware that they receive measurably higher doses of radiation than populations living at similar latitudes in other parts of the world. The radiation doesn't announce itself. There are no warning signs, no visible evidence, no immediate symptoms. It's a silent accumulation, year after year, generation after generation. The truly disturbing aspect is not merely that the anomaly exists, but that so few people know about it. Ask a random person on the streets of Rio about the South Atlantic Anomaly, and you'll likely receive blank stares. The phenomenon remains largely confined to scientific literature, aviation safety meetings, and the quiet concerns of aerospace engineers. Public health officials rarely discuss it. City planners don't factor it into their considerations. The invisible threat doesn't inspire the kind of immediate fear that drives policy changes or public awareness campaigns. It's too abstract, too slow-moving, too technical, and so it persists, known only to specialists while millions remain oblivious. Rio de Janeiro presents perhaps the most striking example of this disconnect between risk and awareness. The city curves along its famous beaches, Christ the Redeemer watching over Sugarloaf Mountain, tourists and locals alike enjoying what seems like paradise. Yet this paradise sits directly beneath one of the most intense radiation zones on the planet's surface. During solar storms, when the sun ejects massive clouds of charged particles toward Earth, the radiation penetrating through the anomaly intensifies dramatically. On these days, airline crews flying over the region receive radiation doses equivalent to multiple chest X-rays in a single flight. Satellites passing through the anomaly often switch to safe mode, shutting down sensitive instruments to avoid damage. And the people below, the millions in their apartments and offices and schools, receive their share too, completely unaware that the sky above them has temporarily become more hostile. Telecommunications companies operating in the region have learned to adapt. The engineers at these firms understand what the public doesn't. They build redundancy into every system. Critical data centers in São Paulo feature backup systems for the backup systems, layers of protection against the electronic disruptions that strike with frustrating regularity. A network engineer who spoke on condition of anonymity described the challenge as fighting an invisible enemy. Equipment fails in patterns that correlate precisely with solar activity, he explained, but explaining this to clients or the public sounds like science fiction. So the companies absorb the costs, replace the damaged components, and maintain the infrastructure that keeps a modern megacity connected to the world. Aviation incidents tell a more dramatic story. While major catastrophes remain rare, the accumulation of minor failures, close calls, and unexplained malfunctions creates a troubling pattern. A commuter flight approaching Buenos Aires in 2012 experienced total GPS failure and partial instrument blackout during final approach. The crew executed a successful emergency landing using visual references and ground-based radio beacons, the kind of old-fashioned navigation that modern pilots rarely practice. The aircraft was thoroughly inspected after landing. Every system tested perfectly. No fault could be identified. A cargo pilot flying between Brasilia and Sao Paulo keeps a personal log of instrument anomalies he's experienced over the years. The entries span more than a decade, brief notations of compass deviations, radio interference, transponder failures, and electronic quirks that appear and disappear like ghosts in the machine. He's shared this log with exactly 3 people, all fellow pilots, all of whom fly regularly through the same airspace. They've compared notes. The patterns match. The interference intensifies during solar storms. Certain altitudes seem more prone to disruption than others. And when they've tried to bring these concerns to officials, they've been met with reassurances that all incidents are being monitored, that safety margins remain adequate, that there's no cause for alarm. But the pilots themselves take precautions. Some request route modifications when space weather forecasts predict heightened solar activity. Others perform extra pre-flight checks on backup systems before entering the anomaly zone. They maintain vigilance in ways that passengers never see, an invisible layer of additional attention paid to instruments that might fail in ways that normal training doesn't fully address. Computer systems throughout the region experience what technicians call soft errors. Random bit flips, where a 0 becomes a 1 or vice versa in computer memory. These errors occur when radiation particles strike silicon chips, causing tiny electrical disruptions that can corrupt data or crash programs. In most parts of the world, such radiation-induced errors are rare enough to be negligible. Beneath the South Atlantic Anomaly, they happen with sufficient frequency that specialized error correction protocols become necessary. Banks, hospitals, government facilities, any institution that depends on reliable computing must account for this elevated baseline of random failures. A data center manager in Sao Paulo described implementing radiation-hardened memory modules in critical servers, the same technology used in satellites, because standard commercial hardware proved insufficiently reliable. The cost difference is substantial, but the alternative is accepting a higher rate of unexplained system crashes and data corruption. Most customers never learn the real reason their service provider invests in such expensive infrastructure. It's easier to cite general reliability concerns than to explain that the city exists beneath an invisible radiation field. The medical implications remain frustratingly unclear. Researchers have attempted to determine whether populations living beneath the anomaly experience higher rates of certain cancers or other radiation-related health effects. The studies produce contradictory results, complicated by the countless other variables that affect human health. The additional radiation dose from the anomaly, while measurable, remains relatively small compared to other sources of background radiation. Whether this chronic, low-level exposure accumulates into meaningful health impacts over decades or generations is a question without a definitive answer. What is certain is that flight crews who regularly transit the anomaly receive elevated radiation, doses that aviation authorities now monitor and limit. Pregnant women working as flight attendants on South American routes are often reassigned to avoid excessive fetal exposure. Pilots approaching career exposure limits might find their routes adjusted to reduce time spent flying through the most intense zones of the anomaly. The aviation industry takes these precautions seriously because the radiation is real, measurable, and significant enough to warrant protective measures. Yet the same concern doesn't extend to the general population below. Perhaps because people on the ground receive lower doses than aircrew at altitude, or perhaps because the political and economic complications of acknowledging widespread radiation exposure to major population centers proves too daunting, the public conversation remains almost non-existent. The threat stays silent, known but unspoken, managed by specialists but hidden from the millions most affected. Buenos Aires adds another 12 million people to the count of those living beneath the anomaly. The city pulses with culture and life, tango in the streets, cafes filled with passionate conversations, a European grandeur transplanted to South America. The anomaly doesn't respect any of this. It bathes the city in the same elevated radiation as everywhere else in the zone, indifferent to human achievement or aspiration. The invisible nature of the threat makes it uniquely disturbing. We fear what we can see, what we can feel, what announces itself with obvious danger. A storm you can watch approaching. An earthquake you can feel shaking the ground. But radiation at these levels offers no sensory warning. You cannot see it, smell it, taste it, or feel it. It passes through your body, leaving no immediate trace, no pain, no indication that anything unusual has occurred. Only specialized instruments reveal its presence, and only over time might its effects potentially accumulate into something measurable. This creates a strange, psychological space where the rational mind understands a threat exists, while the emotional mind struggles to engage with something so abstract and imperceptible. It's the same difficulty people face comprehending climate change or pollution, or any danger that operates on scales too large or too slow for our evolved threat detection systems to properly register. We're built to fear the predator in the grass, not the invisible particles raining down from a weakness in Earth's magnetic field. And so life continues beneath the anomaly. Millions of people living their lives, the cities growing ever larger, the aircraft continuing their routes through hostile sky, the telecommunications networks managing their invisible battles against radiation-induced failures, and almost nobody discussing the uncomfortable truth that some of the world's greatest cities occupy a position of permanent vulnerability to a threat that most people... The South Atlantic Anomaly doesn't ask for acknowledgement. It simply persists, a hole in our planetary shield, a silent reminder that the Earth's protective systems are neither uniform nor invulnerable, and that millions of us have built our homes and lives directly beneath one of its weakest points. The map on Dr. Elena Petrov's monitor had changed again. For the third time in as many months, she adjusted the red boundary marking the South Atlantic Anomaly's perimeter, watching as it crept inexorably westward across her screen. 20 kilometers per year. The number seemed almost trivial when you said it out loud, barely the distance of a half marathon. But when you understood what was moving, when you comprehended the sheer scale of Earth's magnetic field deforming like a diseased organ, that number transformed into something that could keep you awake at night. The South Atlantic Anomaly had always been there, a weakness in our planet's magnetic shield where the protective barrier dips closer to Earth's surface, allowing higher levels of radiation to penetrate. Satellites passing through this region had been experiencing glitches since the space age began. Astronauts aboard the International Space Station routinely reported seeing strange flashes of light when traversing the zone, cosmic rays colliding with their retinas, their bodies absorbing radiation doses that mission planners carefully tracked and limited. But the anomaly had been stable, predictable, a known hazard that engineers designed around. Not anymore. Elena pulled up the historical data, watching the animation she had created play across her screen. The anomaly in 1970 was a neat oval off the coast of Brazil, well-defined and contained. By 2000, it had begun to stretch, elongating like taffy being pulled by invisible hands. By 2010, the expansion had accelerated. Now, in 2025, the anomaly covered nearly twice the area it had occupied just 2 decades earlier, and its western edge was pushing toward the South American continent with relentless determination. She zoomed in on the drift pattern. 20 kilometers per year westward, but that was just the average. Some portions of the boundary moved faster, surging ahead in unpredictable spurts that defied their models. The growth wasn't uniform either. The anomaly was developing lobes, extensions that reached out like the pseudopods of some microscopic organism, probing, expanding, searching for new territory to consume. The really terrifying part was what it might mean. Elena opened the file she had been avoiding, the one marked with the innocuous label that belied its apocalyptic contents. Pole reversal scenarios. Her colleague Marcus had sent it to her at 2 a.m. 3 weeks ago with a message that read simply, "We need to talk about this." Earth's magnetic poles had flipped before, many times throughout geological history. The evidence was written in rocks around the world, ancient lava flows that had cooled and trapped the direction of the magnetic field at the moment of their solidification. These stones revealed a history of chaos, a magnetic field that had reversed itself hundreds of times over millions of years. North becoming south, south becoming north, the planet's internal dynamo stuttering and reorganizing itself in ways that scientists still didn't fully understand. The last major reversal happened 780,000 years ago, an event called the Brunhes-Matuyama reversal. Humanity's ancestors walked the Earth during that transition, though they left no records of what they witnessed, no descriptions of whether the northern lights blazed across equatorial skies, or if navigation by lodestone became impossible. The reversal before that occurred 2.58 million years ago. The gaps between these events varied wildly, from less than 100,000 years to millions. There was no reliable schedule, no warning system. The only certainty was that it would happen again. And the South Atlantic Anomaly, according to a growing chorus of concerned scientists, might be the first symptom. Elena clicked through the computer models that Marcus and his team had developed. The first showed the current state of Earth's magnetic field, a smooth dipole with field lines arcing from pole to pole, a protective cocoon wrapping the planet. The second model advanced the timeline 20 years, incorporating the observed drift and expansion rates of the anomaly. The red zone of weakness had grown substantially, now covering most of the South Atlantic and pushing deep into South America. Satellite failures in the region had tripled. Third model made her stomach clench. 50 years forward, and the anomaly had split. Two separate zones of weakness now pocked the magnetic field like ulcers, one still over the South Atlantic, grown massive and unstable, the other having butted off and drifted toward the Indian Ocean. The magnetic field strength between them had degraded by 40%. Model 4, 100 years ahead, showed a nightmare. Multiple anomalies scattered across the globe. The dipole structure wobbling, field lines tangling into chaotic knots. The smooth protective bubble had become lumpy, irregular, shot through with holes where cosmic radiation poured through unimpeded. And this wasn't wild speculation. This was based on paleomagnetic data, on what the rocks told them about how previous reversals had begun. The field didn't just flip overnight. It weakened. It developed multiple poles. It writhed in confusion, sometimes for thousands of years before settling into a new configuration. Or, and this was the part that made Elena's hands shake when she thought about it too long, it could collapse almost entirely for a period. Some evidence suggested that during past reversals, Earth's magnetic field had diminished to just 10% of its normal strength. 10%. The shield that protected all life on the surface reduced to a thin, tattered curtain that would barely slow the onslaught from space. She opened another file, this one compiled by engineers and infrastructure analysts who had been asked to model the consequences. The document was titled Technology Cascade Failure Scenarios. Someone had a gift for understatement. The global positioning system would be the first casualty. GPS satellites orbited at 20,000 kilometers, well above the protective layers of Earth's atmosphere. They were already vulnerable to solar storms, their delicate electronics susceptible to the charged particles that occasionally erupted from the sun's surface. During a major solar event, GPS accuracy degraded. Positions became uncertain. Timestamps, the synchronized heartbeat that 1,000 technologies depended on, began to drift. Now imagine those satellites trying to function as the magnetic field weakened, as the anomalies expanded and multiplied, as the radiation environment in near-Earth space transformed from a manageable hazard into a constant bombardment. One by one, the satellites would fail. Bit flips caused by cosmic rays would accumulate faster than error correction systems could handle. Solar panels would degrade under the increased radiation. Star trackers, the optical systems that helped satellites orient themselves, would be blinded by the energetic particles creating false signals. The constellation that provided navigation for everything from commercial airliners to container ships, from precision agriculture to emergency services, would begin to crumble. And GPS was just the beginning. Communications satellites, weather satellites, Earth observation platforms, the entire orbital infrastructure that modern civilization had come to depend on. All of it existed in an environment that was about to become exponentially more hostile. The report estimated that during a severe magnetic field weakening, satellite lifespans would decrease from decades to months. The economics alone would be devastating. The cost of constantly replacing orbital assets would be unsustainable. Some services would simply cease to exist. But the satellites dying would be a manageable disaster compared to what would happen on the ground. The weakened magnetic field wouldn't just endanger objects in space. It would fundamentally alter how Earth interacted with the sun. Solar storms happened regularly. Great eruptions of plasma hurled into space by the roiling magnetic chaos at the sun's surface. When these clouds of charged particles reached Earth, our magnetic field normally deflected most of them, channeling the remainder toward the poles where they created the auroras, beautiful light shows that marked the boundary of our protective bubble. During particularly intense storms, some particles penetrated deeper, occasionally disrupting communications and, in rare cases, damaging power infrastructure. The Quebec blackout of 1989 had been caused by a solar storm, 57 seconds from coronal ejection to total grid collapse, 6 million people without power in March, in winter, because the induced currents from the geomagnetic disturbance had overwhelmed, transformed. That storm had struck when Earth's magnetic field was at full strength. Now, imagine a similar event, or worse, a Carrington-class superstorm like the one that had hit in 1859, but arriving when the field had degraded to a fraction of its normal intensity. The particles wouldn't be deflected. They would pour straight down into the atmosphere, inducing massive currents in anything conductive. Power lines would become conduits for electromagnetic chaos. Transformers, the critical and often irreplaceable components that stepped voltage up and down across the distribution network, would blow by the thousands. Not just in one province or one region, but globally, wherever the storm struck and the field failed to protect. The cascading failures would unfold with terrifying speed. Power grids were interconnected, each part dependent on every other part. When sections failed, the load redistributed to the remaining functional areas, often overloading them and triggering additional failures. Engineers called it cascade collapse, and they had seen it happen from purely technical glitches. Add a solar megastorm penetrating a weakened magnetic field, and the scenario shifted from blackout to something more permanent. Restoration required replacement transformers, massive pieces of equipment that took months or years to manufacture. With global supply chains disrupted by the same event, with demand suddenly overwhelming every manufacturer simultaneously, the timeline for recovery stretched from months to years, possibly decades. Elena read the summary paragraph again, though she had it practically memorized. A major solar storm impacting Earth during a period of significant magnetic field weakening could result in the simultaneous failure of power infrastructure across multiple continents. Recovery timeframes measured in years would lead to secondary collapse of water treatment systems, food distribution networks, medical services, and financial systems. Estimated casualties from a worst-case scenario range from hundreds of millions to over 1 billion within the first year. Then there were 1 billion people. The number was so large it became abstract, meaningless. Elena tried to picture it, and couldn't. She could picture her neighborhood without power. She could imagine her city dark and cold. She could extend that to her country, to her continent. But the whole world, the entire technological civilization that 8 billion people depended on, reduced to a pre-industrial state in a matter of hours? It was the stuff of apocalyptic fiction, except it was written in sober academic language by people with doctorates and decades of experience. And it might already be starting. The anomaly was moving, growing, possibly fragmenting. The computer models showed it clearly, trajectories that led toward magnetic chaos, toward a pole reversal that could leave humanity exposed during the very period when we were most dependent on technologies that required a stable, protective, magnetic field. There were uncertainties, of course. The models could be wrong. The anomaly might stabilize, might even shrink. Pole reversals took thousands of years usually, and perhaps the current changes were just normal variation, nothing to panic about. But the data kept coming in, and it kept showing the same trends. Growth. Wow. Drift. Acceleration. Elena closed the files and stared at her reflection in the dark monitor. Outside her office window, the city glittered with electric light, every building, every street lamp, every device taking for granted the complex web of technology that made modern life possible. Navigation systems guided traffic. Communication networks connected billions of people. Power flowed endlessly from distant generators through hundreds of thousands of miles of wire. And above it all, invisible and mostly forgotten, Earth's magnetic field stood guard. Had stood guard for all of human history, deflecting the cosmic radiation that would otherwise sterilize the surface. That guard was wavering. The South Atlantic Anomaly was just the visible symptom of something happening deep in Earth's core, in the churning liquid iron that generated the magnetic field through processes that still weren't fully understood. The planet's protection was failing, and there was nothing anyone could do to stop it. You couldn't repair Earth's magnetic field. You couldn't strengthen it or redirect it. You could only watch and measure and model and hope that the worst-case scenarios remained theoretical. She thought about the people walking below her window, worried about ordinary things, traffic and deadlines, and what to have for dinner. None of them knew that above their heads, the anomaly was drifting westward at 20 kilometers per year, that in the silent depths beneath their feet, the iron core was reorganizing itself towards some new configuration. They didn't know that their GPS might fail, that their satellites might die, that a solar storm could arrive tomorrow and find Earth's defenses compromised, vulnerable in a way that had never mattered before because there had been nothing to destroy. Ancient humans had survived pole reversals without even noticing. Modern humans had built a civilization that might not survive a week. Elena saved her work and shut down her computer. The models would still be there tomorrow, the projections and scenarios and nightmare futures. The anomaly would continue its westward march, indifferent to human concerns. And somewhere in the depths of Earth's core, in the darkness and heat and impossible pressures, the magnetic dynamo continued its ancient, inscrutable work, preparing perhaps for a change that would reshape the world above. The data arrived quietly, tucked into a routine research paper published in 2006. A team of Brazilian scientists had been studying flight attendants working the São Paulo to Johannesburg route, the trajectory that cuts directly through the heart of the South Atlantic Anomaly. What they found should have made headlines around the world. Flight crew members on this route showed cancer rates 47% higher than their colleagues flying other international paths. 47%. But the study barely registered in the scientific community, and the general public never heard about it at all. Dr. Helena Cardoso led that research team. She spent 3 years tracking health outcomes for 238 cabin crew members, comparing blood work, conducting interviews, reviewing medical histories. The pattern was undeniable. Breast cancer, thyroid cancer, melanoma, leukemia, all occurring at rates that couldn't be explained by lifestyle factors or chance. When she submitted her findings to international aviation safety boards, she received polite acknowledgments and nothing more. When she tried to secure funding for a larger study, her grant applications were quietly denied. She told a colleague, off the record, that she'd been advised to focus her research elsewhere. That certain questions made certain people uncomfortable. The mechanism is brutally simple. The South Atlantic Anomaly represents a weakness in Earth's protective magnetic shield, allowing charged particles from the Van Allen radiation belts to dip closer to the planet's surface. At cruising altitude, passengers and crew receive radiation doses significantly higher than anywhere else in commercial aviation. A single flight through the anomaly exposes you to roughly the same radiation as a chest X-ray. Flight attendants working this route 5 times a week absorb that exposure again and again, year after year. The damage accumulates in their cells, in their DNA, in the delicate machinery that keeps tumors from forming. But the crew members can choose different routes, can change careers, can escape. The people living beneath the anomaly have no such option. NASA conducted a study in 2014, one that most people have never heard of. Researchers at the Johnson Space Center wanted to understand how the South Atlantic Anomaly affected astronauts aboard the International Space Station. The ISS passes through the anomaly multiple times each day, and mission controllers had noticed something disturbing. Astronauts reported seeing bright flashes, even with their eyes closed, strange phosphorescent lights dancing in their vision. These were cosmic rays passing directly through their eyeballs, through their optic nerves, damaging cells along the way. The NASA team decided to send fruit flies to the space station. Drosophila melanogaster, the humble fruit fly, has been a workhorse of genetic research for over a century. Their short life cycles and well-mapped genomes make them perfect for studying mutations. The scientists sent up multiple generations of flies, carefully shielded containers to protect control groups, and sensitive equipment to measure radiation exposure during SAA passages. The results were classified for 2 years. When portions of the study finally reached the public domain, the data had been heavily redacted. What remained told a chilling story. Fruit flies exposed to South Atlantic Anomaly radiation showed mutation rates 3.8 times higher than the control group. 3.8 times. Genetic damage appeared in reproductive cells, meaning these mutations would pass to offspring. The researchers noted peculiar chromosomal breaks, unusual patterns of DNA damage, that didn't match typical cosmic ray exposure. The implications were obvious and terrifying. If fruit flies experienced this level of genetic damage, what was happening to astronauts? What was happening to the 70 million people living beneath the anomaly's shadow? Dr. Robert Chen worked for NASA's Radiation Health Division from 2009 to 2016. He was part of the team analyzing astronaut health data, looking for long-term effects of space radiation exposure. In 2018, 2 years after leaving the agency, he gave an interview to a small science podcast. He spoke carefully, never quite making direct accusations, always prefacing his statements with phrases like the data suggests and one interpretation might be. But his message was clear. NASA had identified concerning health trends among astronauts who'd logged significant time aboard the ISS during solar minimum periods, when the SAA's effects were strongest. Elevated cancer rates, yes, but also more subtle changes. Accelerated aging markers in blood work, unusual patterns of cellular damage, cognitive effects that persisted years after missions ended. The agency had assembled a special task force to investigate. That task force disbanded after 18 months, their final report never made public. Dr. Chen mentioned, almost as an afterthought, that similar patterns should theoretically appear in populations living under the anomaly at ground level. The radiation exposure would be less intense than in orbit, but constant, generational, affecting millions over decades. He said someone should really study that. He said he tried to get approval for exactly such a study. He didn't say what happened to his proposal, but his tone suggested everything. The podcast episode was downloaded 43,000 times in the first week. Then it disappeared. The hosting service removed it, citing unspecified terms of service violations. Dr. Chen declined all subsequent interview requests. In Argentina, researchers at the University of Buenos Aires have been quietly tracking cancer statistics in Patagonian provinces for the past 15 years. They don't advertise this work. They publish in obscure journals, present at small regional conferences, keep their heads down. But the data exists, and it tells a story that becomes harder to ignore with each passing year. Cancer rates in provinces beneath the anomaly's core have risen steadily since the 1990s, outpacing national trends even after controlling for industrialization, pollution, and lifestyle factors. Thyroid cancer shows particularly dramatic increases. So does childhood leukemia. The researchers have mapped these rates against the anomaly's shifting position, watching as cancer clusters drift southward, tracking the magnetic field's slow migration. One of these researchers, who spoke on condition of anonymity, described their work as documenting a crime in progress, an uncontrolled radiation experiment conducted on millions of unwitting subjects. She said they'd approached health ministries, international organizations, anyone who might listen. The response was always the same. Concern expressed, importance acknowledged, further study needed, funding not currently available. She said it felt like screaming into a void. The biological mechanisms of radiation damage are well understood. High-energy particles slam into cells, tearing through DNA strands, creating breaks and mutation. Usually, cellular repair mechanisms fix this damage. But radiation overwhelms these defenses, creating more breaks than the cell can properly repair. Mistakes creep in. Mutations accumulate. Most are harmless. Some are deadly. A few, the worst kind, turn normal cells into cancer cells. This happens whether the radiation comes from a nuclear accident, a medical X-ray, or the South Atlantic Anomaly. The source doesn't matter, only the dose and duration of exposure. People living under the anomaly receive low-level exposure constantly. Not enough to cause immediate symptoms. Not enough to trigger radiation sickness. Just enough to steadily, relentlessly damage their DNA. Month after month, year after year, generation after generation. And here's the truly horrifying part. We won't know the full extent of this damage for decades. Radiation-induced cancers typically appear 10 to 30 years after exposure. Genetic damage can remain silent for generations before manifesting in unexpected ways. We're watching the opening act of a tragedy that will unfold across the rest of this century and beyond. The people being exposed today won't see the consequences until mid-century. Their children and grandchildren will carry mutations we can't yet detect or predict. Scientists at the Brazilian National Institute for Space Research have identified another disturbing pattern. They've been monitoring mutation rates in plants and insects across regions of varying SAA exposure intensity. The data shows a clear correlation. Higher exposure equals higher mutation rates. They've documented unusual genetic variations in moth populations, aberrant growth patterns in soybeans, chromosomal abnormalities in wild grasses. The lead researcher on this project tried to publish their findings in a major international journal in 2019. The paper was rejected, not because of methodological flaws or insufficient data, but because, as one reviewer put it, the implications were too extraordinary and would require extraordinary evidence to prove. The researcher resubmitted to other journals. Same result. The paper remains unpublished, the data gathering dust while the mutations continue. There are other scientists asking these questions, conducting quiet research, trying to understand what's happening beneath the anomaly. Most prefer not to speak publicly. Some have been explicitly warned that their careers depend on discretion. Others have simply learned that certain topics don't attract funding, don't advance careers, don't make you popular with administrators or government liaisons. But the data exists. In university databases and research archives, in preliminary studies and abandoned grant proposals, in the private files of concerned scientists who know something is wrong but lack the power or platform to do anything about it. The South Atlantic Anomaly is growing. Satellite measurements show it expanding and weakening, allowing more radiation through to lower altitudes. Climate models, the ones that include magnetic field variables, suggest this trend will continue. More people will fall under its influence. Exposure levels will increase. The experiment grows larger. And still, there's no comprehensive study of health effects on ground populations. No long-term tracking of genetic damage. No serious effort to understand what decades of chronic low-level radiation exposure might mean for 70 million people, and counting. Just scattered research efforts, inconclusive data, and a collective institutional unwillingness to confront the possibility that we're slowly irradiating a significant portion of South America's population. The silence itself is damning. In an age where we study everything, measure everything, track health outcomes for every conceivable variable, this gap stands out. It's not ignorance. It's choice. A decision, made repeatedly at every level, to not look too closely at what's happening beneath the anomaly. Because if we looked, really looked, we'd have to acknowledge an uncomfortable truth. We'd have to admit that millions of people are being exposed to elevated radiation through no fault of their own, with potentially devastating long-term consequences, and we're doing nothing about it. We can't fix the Earth's magnetic field. We can't make the anomaly disappear. We can't undo generations of exposure. All we can do is watch and wait and hope that the scientists who lose sleep over this are wrong. Hope that the elevated cancer rates are statistical flukes. Hope that the mutations in fruit flies don't translate to humans. Hope that decades from now we won't look back on this moment and wonder why we didn't act when we still had time. But hope isn't data. And the data, what little we have, what little they've allowed us to see, suggests we should be terrified. The question keeps the scientists awake at night. Why is the South Atlantic Anomaly accelerating? For decades, researchers tracked the anomaly's westward drift at a steady, predictable pace. But something changed. Recent measurements show the movement has quickened, the weakened zone expanding faster than models predicted. The anomaly now stretches further than ever before, its boundaries pushing outward like a wound that refuses to heal. And no one can explain why. The intensity fluctuations remain equally baffling. Satellites pass through the anomaly and encounter radiation levels that spike without warning, dropping and surging in patterns that defy prediction. One day the zone appears relatively calm. The next, it erupts with particle bombardment that sends spacecraft tumbling into emergency protocols. These unpredictable variations suggest something deeply unstable is happening beneath our feet, in the swirling currents of molten iron that generate Earth's magnetic shield. But current technology cannot penetrate deep enough to see what's really occurring down there in the darkness. Perhaps most disturbing is what we don't know about similar zones elsewhere. The Earth's magnetic field wraps around our entire planet, yet we monitor only a fraction of it. Vast stretches of ocean remain unobserved, their magnetic characteristics unmeasured. Could other anomalies be forming right now in these blind spots? Could weaknesses be developing over the Pacific, over the Indian Ocean, over the polar regions, and we simply haven't detected them yet? The gaps in our monitoring systems are staggering. Most of the data about the South Atlantic Anomaly remains locked behind classified walls. Space agencies guard their research closely, releasing only sanitized versions to the public. The full extent of satellite failures, the true radiation levels, the complete picture of how rapidly conditions are deteriorating, all of this stays hidden behind security clearances and redacted reports. We build our entire civilization on technology that one good solar storm could destroy, and the South Atlantic Anomaly is the crack in our armor. When the next superstorm comes, and it will come, that weakened zone might be where our technological world finally breaks, and we have absolutely no way to stop it. That's where this journey ends for tonight. If you made it all the way here, subscribe and hit the bell for more long-form stories like this. Check out the videos on screen for more right now. Drop your own experiences in the comments below. Thanks for listening, and I'll see you in the next one.